Good morning and welcome to our course on Introduction to Mechanical Micromachining Processes. In the last class, we have seen some of the classifications of the different micro fabrication processes, and those processes classification we have done in terms of the material by which we can do different type of shaping, whether we remove the material from the workpiece, we add the material layer by layer, we contain the material mass and we deform the surface so that we can get different shapes by casting and different molding processes, or we join the different materials, we have ready made shapes. So, these are the different classification, and then we have classified this material in terms of the MEMS product or the lithography base and non lithographic processes or called the non MEMS. So, here also we have seen classification, and one category was related to the etching and lithography and deposition, while in other case it was related to the casting, laser beam machining and the micromechanical processes. Third classification we have seen in the similar line, but there was a additional feature or additional component was the handling, mounting, metrology and the quality control. So, these are the way we classified these different type of machining processes, and then we started with the comparison between the MEMS processes and the mechanical micromachining processes, that how these processes are different from each other. So, first one was the workpiece material. We have seen the silicon and some metals can be machined by the MEMS base, that is by lithographic processes or the etching processes, but here we have very vast range of the material which can be machined by mechanical processes. And then we have seen the component geometry, it is a planar and 2.5D, and we have seen the how to define 2.5D geometry. That means your Z height is very small or it can be neglected compared to the X and Y dimension, and these are the some of the one components of 2.5D, and this is the one component for 3D part. So, this is the geometry, and other than that there is a one particular thing is 2.5D machining. So, what is this 2.5D machining? We know the 3D machining, we know the 2D machining also, but what is this in between these two? Now, if you consider, and let us see that how we can define this 2.5D machining. So, this is consider x direction, y direction and z direction. Now, consider your tool is located here. So, this is your tool, it is rotating and it is at this location, and you want to go to this location. This is the tool, and this is the target location. Now, there are many ways by which you can go to that location. So, our tool will directly go from here to here or it will go in this direction. So, first let us see what is 2.5D machining. So, 2.5D means that tool can move in two direction simultaneously. So, now suppose our tool is here, then tool will move in this direction. So, when it is moving in this direction, it is moving in x and y, and then it moves in the z direction. So, this is called z direction. In same way, what it can do, that it can move in this direction also. So, this movement is in two direction, one is in the our y direction is fixed. So, it is in x and z direction, and once it reach here, then it will move in the y direction. So, in that way we know that your tool is moving simultaneously in only two axes, either in xy or xz, or it is in yz direction, but after once it reach, then only it will move in the third direction. So, that is why it is called 2.5D machining. And now, what is 3D machining? That is 3D. So, now our tool is located here, and if it directly goes from here to here, now you know that it is moving in all these three directions. So, this is moving in x, y and z, all three directions, because this is the shortest path by which it will reach to this location. So, once it is moving in this direction, it is covering this path also, and once it is going down, it is covering z path also. So, when your tool is moving, 3D machining means tool can move in all three direction or axis together. So, this is called 2.5D machining, and this is called 2.5D geometry. So, this is the difference between these two different terminologies. Now, some other parameter, relative accuracy. Relative accuracy is here 10 raised to minus 1 to 10 raised to minus 3, but here that range is little bit large. So, now what is relative accuracy? So, now here relative accuracy means this is the tolerance divided by the object size. Now, if you see this particular graph, you know that this is the nano electromechanical system. Nano electromechanical system. This is known, it is a micro electromechanical system, and this is the our processes which we are covering here, and this is the conventional and the ultra precision manufacturing processes. Now, this is the object size, and here this is the object size. So, here you can see it is very small, it is in 10 raised to minus 9 millimeter size. This is in terms of 1 millimeter, and this is in terms of meter, and this is smaller in this particular direction. So, now how we can define this thing? So, now suppose you have one cylinder. Now, this length consider 50 mm, and this is the diameter, and that let us consider this is a 20 millimeter diameter. Now, when you are telling a 20 millimeter diameter, and this actually it is difficult to fabricate with the same dimension. So, what we generally do that we give a tolerance. So, 50 plus minus we put something like 0.001 or 0.001, something like that. So, it is something like if it is like that. So, if dimension is within 50.001 to 49.999, that means this is a acceptable dimension with respect to the fabrication process. So, now if you see this particular thing, this is called object size. So, now if object size is this much, and you can easily get the dimension at the micron. Suppose it is a 50 by 20, then you consider, let us consider only the diameter, that you need a length, let us assume the length exactly perfectly you are getting 50 millimeter, but it is not the case. But right now let us consider it is possible. Now, let us consider on dimension of the diameter. Suppose it is a 20 millimeter diameter, and if you can create a diameter, your requirement is 20 millimeter, your machine is giving 20.0001. So, it is in millimeter. So, here you can say it is a 0.1 micron tolerance you can achieve in this particular case. Now, it is in millimeter to this one. it is possible only in the bigger size. Now, when you turn it, by turning process you cannot create such a high tolerance. So, this is the turning operation first operation is turning, and once turning is over, then what you have to do? You have to do cylindrical grinding. And after cylindrical grinding, you may need some type of belt grinding to reach to this location. That is called abrasive belt grinding. And after that you can achieve this. So, now you can see that it has passed through many operations. One operation is this, second operation is this, and this is the third operation. Now, you can see the dimension of this and number of operations. It is possible to perform a multiple or sequential operations, that is dimension is in millimeter size. So, you can see the component, some type of post processing is possible. So, these all things are called the post processing. So, this is and this particular process. So, these processes are the post processing. So, this post processing is only possible because dimension is very large, and you can easily see and you can perform different operation on the top of it. But here problem with this particular component is, that means you are able to do the dimension control in this case very easily. But if you see this particular part, now consider we have a shaft diameter of a 200 micron and length consider around 2 millimeter. Now, we have done a turning operation here. So, first operation is turning, similar to earlier operation, but it is in micro turning. And once it is over, now you cannot perform, it is very difficult to perform the third operation, that is called cylindrical grinding. And other operation like a abrasive belt grinding or some other processes by which you can get the required amount of tolerances here. So, why this relative accuracy is very less in this case? Because you will not get a second chance of improvement of the geometry or the dimensional accuracy. So, here we can write difficult to perform secondary operations to reduce the dimension variation. Right. So, this is what is happening in this particular case. So, now we know that our dimension is in 200 micron like this here, and suppose your tolerance is also in micron, because here maximum it can go with a sub-micron level. So, difference between the actual dimension, that is what we are telling, that this is the size of the actual size of the object, that is a 200 micron, and our feature tolerance is also in micron, or consider it is a 1 micron to 0.1 micron or 0.01 micron, but still everything is in micron. So, if you take the ratio of this thing, it will be very small in this case. But if you see in this micromechanical, our object component, suppose we can easily get some component of a millimeter size. Suppose here it is a 1 millimeter is the diameter of this particular part, and you can easily get the different type of feature or different type of surfaces here by finely tuning the processes, and you can easily get the from 1 millimeter you can get 0.001 micron also. So, in this particular case, now you can see the starting dimension is 200 micron here, but here starting dimension is 1 millimeter, and you can see the tolerance is in 1 micron to like that. Here also you can get 0.01 to 1 micron, but the difference is very very large. So, that is why we are getting a very large relative accuracy compared to the MEMS product. Now, another one the production rate, but production rate it is very very high in terms of MEMS product, because now these all processes are chip based. Now, we can say that this is called this is a silicon wafer, and these are the individual chips. Or it is called integrated circuit or IC chips. Now, you can see that whatever the diameter of this silicon wafer, you can create a many chips simultaneously, because you do not need to do a single operation. Now, you can see these are the small components. Once all chips are ready, then you can actually cut these chips separately and then use this chip for a separate processor. So, here the production rate is extremely high, and this is the reason that our mobile phone and electronics items are day by day their power is very very high and the cost is very very low, because this is in mass production. But if you see our machine, that we use a milling operation, then drilling operation and turning operation, and this all the operations can be performed in a sequence way. That means, you cannot perform both the operation milling and turning simultaneously. To fabricate this component, one tool will interact with the surface, and then once part is over, then only you can fabricate the next one, and again you need to spend some time in the setting of the component, again the measurement and everything. So, that is difficult in this case. That means, the mass production is very very low. That means, here production rate is low and comparatively very high in the MEMS processes. Now, control is process control is feed forward, and it is feedback control. Now, what is this? Because in MEMS product, now we have lot of processes, which is a lithography, then we do etching process, then deposition. So, these processes continue till you achieve the required shape or the required dimension of the feature. So, this process is these steps continue till you achieve the required dimension. So, here order will not be much problem, because etching may take place first also, this may come first, this may come first, like this, but it will continue, because in a single step you cannot fabricate the process. So, feed forward processes are there, that you can control the sequence only. That means, what it is coming out of this, you cannot actually regulate that particular thing. That suppose you are fabricating, you are making one mask and you are fabricating one etching process here. That is, by etching process you are fabricating some features here, and once etching process is over, that means, whatever process has come, that whatever product has come, that product will go to the next station. So, there is no way you can actually refine this particular process or earlier process. So, that is why it is called feed forward processes. What is feedback processes? Suppose we are making one component and this is our cutting tool, and it is rotating. So, we have in our hand speed feed and depth of cut. And we do this machining simultaneously, you are putting some sensors also. So, these sensors will give you the feedback. Give feedback of process. So, these sensors can be a force sensor, then current sensor, or some type of acoustic emission sensors. So, once these sensors are there, at that time what here you can do, that you can actually fine tune these processes. The suppose forces are very high, then what it will do, it will reduce the feed and increase the speed also. In that way you can actually control the process in a feedback manner. So, every time whatever sequence is happening here between the cutting tool and the workpiece, at that time that signal will transfer to the input parameters. So, you can refine the process during the machining, but that option is, or that facility, or that particular feature is not available in the MEMS product, because there are many processes available which will process the components separately. But here we are using a milling machine only, and it is equipped with many different type of sensors, and that is the advantage of going with the feedback control. Initial investment is very high, and here it is moderate to low. Initial investment means, here if you see this particular MEMS products, so MEMS products needs many things, that is, one is the clean room. So, clean room itself is very difficult, because you cannot operate this lithographic equipment. Then etching, then Liga process. So, these are the particular processes which need some strict environmental control. So, clean room is a controlled so it is a dust, particles, humidity, noise level, temperature, and many things. Means other than that, there you have to make sure that there is no large variation in the temperature, humidity is also there, dust particles, then how many dust particles are there. So, particles means quantity and size. So, there are different clean rooms are actually rated in terms of the 1000 clean room, then 10,000, or these are the 1000 class, it is known as a class 1, class 1000, then class 10,000, class 1, like that. So, higher this rating, more strict is the control of this particular part. So, this class control, higher the class, more strict, of the environmental parameters. Correct. So, this is where if you see this, there are many processes available, you have to prepare a clean room also, and that is why its cost is very high. Here it is moderate to low, that means you have to spend more money in the process or the buying of the equipment. Equipment, that is machines, and then you need a metrology, that is in both the cases. Because without metrology, because in if you see both the feature size and all the thing, both things are in micron, but here you can go very small in the dimension, that is limited here because we have limitation in the size of the cutting tool also. So, metrology is required in both the cases. So, we are not considering the cost of the metrology, but here the metrology requirement is very little tight here, because the dimensions of the components are also very small. So, resolution and all these things are very tightly controlled, but here you can actually go with a moderate equipment of the metrology also to make sure that dimension can be measurable. Now, whatever we have discussed till now, that was the comparison between the MEMS product and the mechanical product. So, here we have seen that these processes are mostly used for fabrication of the MEMS product, that is mostly electromechanical system. And these products are these particular processes are used for fabrication of different components and features. So, it has its own application, because here it is a complete package. That means, here you consider the sensors, actuators, etc. can be made by these processes, but here of this micromechanical you cannot create a product, but here you can create a component and features. Because suppose you want to make a sensor and you want to create a one type of packaging of the sensors. So, packaging of the sensor can be fabricated by these particular processes. So, in that way it has a different domain and this one has a different domain. This is related to the complete product, but this is related to the component and some of the features. So, let me finish this class here and we will continue from the next slide in the next class. Thank you very much.